Hello, I'm Sokumabe. Today, we talk about our paper, Our Gathering Problem on Spiders, Hardness, FPT algorithms, and PTASes. First, we define the spider. Spider is a D-raised sharding endpoint. The shared endpoint is called center. This is an example of D equals to 5. Each ray is called a leg, and we introduce the distance on it naturally. Our gather clustering problem is defined on metric M and set of users on M. We divide the set of users into clusters and minimize the maximum radius of clusters. And constraint is each cluster should contain at least R users. Here is an example of our clustering problem on Spider. Each blue point is the user. Here is the optimal solution. You can see that each cluster contains at least R equals to 3 users. Various results are known for the algorithm clustering problem. For general metric, 2 approximation polynomial time algorithm and tight hardness result is known. For the line case, the linear time algorithm is known. For spider case, the FPT algorithm of this time is known. Note that this is the algorithm parameterized both by R, the minimum number of users in the cluster, and D, number of legs. In this research, we investigate the case MS spider, and first, we improve the time complexity of FPT algorithm to the FPT algorithm that is parameterized only by the number of legs. We also give PTASes for this case, and this result can be extended to the tree. Furthermore, we prove the NP hardness of the algorithm clustering problem on spider. Since spider is somehow simple metric, this is a surprising result. And this gadget construction automatically means there is no FPTAS. First, we give FPT algorithm. We classify the clusters into 2 cases, multi-leg cluster and single-leg clusters. Multi-leg cluster is the cluster that contains users from multiple legs. The single-leg cluster is the cluster contains users from single leg. The yellow one is multi-leg cluster and the gray one is single-leg cluster. If there is no multi-leg clusters, we can treat the legs independently. And since the independent each leg is line, we can apply linear time algorithm for line. So the combination of multi-leg cluster is essential in this problem. Our first observation here is we can assume that the users in multi-leg clusters are in continuous region, including a center. It is because if 2 clusters crosses like this, we can swap the users without increasing the objective value and without breaking a constraint. So we cut legs at the border of single and multi-leg clusters and assume that there is optimal solution using only multi-leg clusters. That is, we concentrate on the inside of the border. We defined good multi-leg clusters. A multi-leg cluster is good if for leg L and integer k that consists of first k nearest users from center, this ball part, and all users in leg L, this stick part. The important lemma here is if there is an optimal solution using only multi-leg clusters, then there is an optimal solution using a good multi-leg cluster. By repeatedly applying this observation, we can align the multi-leg clusters from inside to outside. That is, take the good matrix cluster and remove it and apply them repeatedly, and we get another good matrix clusters, and so on. This observation leads us to dynamic programming algorithm. We look at the users in increasing order of distance from the center and construct the matrix clusters from inside to the outside in previous order. The state of the dynamic programming is integer ij, user u, and leg subset s that dpisjk is given by the minimum maximum radius of previously constructed clusters subject to I nearest users from center are used, and legs in S, the users on legs in S are also used. And size of current matrix cluster is J, and last user is U. The answer is given by this form. We combine with algorithm for single clusters, and we obtain this time complexity. Note that here, 2 to the power of d is from the choice of S. Next, we give PTASes. The main idea for PTASes is distance rounding and dynamic programming. Distance rounding is simple. Let S be the epsilon fraction of optimal value. We relocate users to the point that is distance from the center by multiple of t. By this relocation, optimal value changes not so much. By this relocation, we can solve this instance optimally by dynamic programming. The important observation here is multiple clusters contains points at most of the epsilon candidate coordinates 0t, 2t, and so on for each leg. By making this number of users distance from the center 0t, 2t, and so on to the key of the dynamic programming, we can write the dynamic programming of order n to the power of order epsilon inverse states. And it is a PTASE. This algorithm can naturally be extended to the tree case. Finally, we prove the hardness result. We prove the hardness via auxiliary problem. Auxiliary problem is defined by the set of integer quadruple called payment duties and integer pairs called payment constraint. And for each payment duty, we choose to pay AI$1 on day PI1 or AI$2 on day PI2. The constraint is we can pay at most $90 before day Bj for each j. Here is an example. The red rectangles represent that we should pay $3 on day 1 or $9 on day 8. And we can pay at most $4 in total before day 2, $11 before day 5, and $21 before day 8. This is one of the feasible solutions. For each color, we chose one payment date, and constraints are satisfied. Our proof outline, proof consists of two steps. First, we prove if auxiliary problem is strong NP-hard, altogether clustering problem is NP-hard on spiral. After that, we prove that auxiliary problem is actually strong NP-hard. Here, strong NP-hard means NP-hard even if input integers are given in unary representation. First, we reduce the auxiliary problem into altogether clustering problem to decide whether optimal solution is L, at most L or not. To do this, we prepare two types of legs, short legs and long legs. Short legs represent the payment constraints, and each long leg represents a payment duty. Here is a short leg. We prepare qj users within distance bj from the center. Intuitively, each user represents $1 of budget on the day equals to the distance from the center. And for each payment duty, we prepare a long leg and locate users like this. Here, the cluster that contains these R users is this or this. And if we cut here, we need 3 additional users from the center by distance, at most 2, on the short legs. If we cut here, we need 5 additional users on the short legs from distance from center, at most 6. This is a construction of gadget. Finally, we prove that auxiliary problem is stronger NP-hard. We prove by reducing it from 1-in-3 problem. One in 3 problem is a variant of 3-stat problem, but each cause should contain exactly 1 true variable. The gadget constructed gadget is complicated, so we don't explain it here in detail. But the proof strategy is to write the 1-in-3 constraint by setting the p-value and q-value like this. By setting coefficients appropriately, we can write the 1-in-3 constraints. And this value is polynomial of input size, so it is the gadget to prove strong NP-hardness. Let us summarize our result. For algebra clustering problem, we gain first FPT algorithm parameterized only by number of legs. It is via structural lemma and dynamic programming. The structural lemma ensures us to construct the clusters from inside to the outside. We also give up PTASes. It is the combination of distance rounding and dynamic programming. Finally, we prove NP-hardness via strong NP-hardness of auxiliary problem. The main open problem is FPT algorithm on trees. We don't know whether it is possible when parameterized by number of edges on trees. Thank you for listening.